Let's talk about cation analysis and the flame test. The cation analysis is a stepwise procedure we do to a solution of cations to identify which cations are present within that solution. The first step is we take a part of that cation solution and we add dilute hydrochloric acid into it. And when we do so, a white precipitate might form. And if a white precipitate forms, it could either be silver chloride, lead chloride, and mercurous chloride. This is actually plumbous chloride, Pb2 plus. Pb4 plus is plumbic chloride. Plumbic. So this is plumbous chloride. All of them are white salts, and thereby, if we were to observe a white color precipitate, we'll be able to determine that either silver ions or plumbous ions or mercurous ions are present within the solution. We can actually differentiate between these salts using secondary titrations, in which we can determine we determine the solubility product of the salt that is precipitated, and via that we can identify which salts have precipitated. Then we filter these precipitates and we obtain the filtrate. The filtrate is acidic because of we virtually added the hydrochloric acid into the solution, and it will precipitate, and then we bubble hydrogen sulfide gas into the solution so that the cations they precipitate as their sulfides. Here these cations are unique because they need a low sulfide ion concentration to precipitate as their sulfides, because the acidic medium ensures that. You see, hydrogen sulfide, it exists when dissolved in water, it exists in this equilibrium where hydrogen sulfide reversibly dissociates to form hydronium ion and virtually hydrogen ions, and bisulfide ion, and the bisulfide ion also dissociates to form a hydrogen ion and a sulfide ion, and it is this sulfide ion that precipitates the cations. When in an acidic medium, the hydrogen ions present is very high, so these equilibrium reactions they shift to the backward directions to the reactant side according to Le Chatelier's principle, and thus a low sulfide ion concentration is formed, and these cations they can precipitate. They are those with the sulfides of these cations have a low Ksp value. They have a low solubility product, and thus they will precipitate in a low sulfide ion concentration. Now enough of that. If we were to observe a black color precipitate, it would mean the presence of either cupric sulfide, mercuric sulfide, plumbous sulfide, or bismuth sulfide. Here both of these are plumbous, but here it's mercurous and here it's mercuric. So if a black precipitate were to be present, we can identify that it's the presence of either the cupric ions, the mercuric ion, the plumbous ion, or the bismuth ion. We can use the secondary titrations based on solubility product to identify which of these are present, and we can do the same for these salts. These are yellow in color. If we were to observe a yellow color precipitate, it could be either of these salts: antimony sulfide, cadmium sulfide, tin sulfide. Well, tin sulfide as in stannic sulfide, and thus we can conclude the presence of either so we can identify that either the arsenic ion is present, or the cadmium ion, or the stannic ion is present. Now these two are easy. If we were to observe a brown or orange color precipitate, we could easily identify that the salts are stannous sulfide or antimony sulfide. If a brown precipitate forms, stannous sulfide is present, and thus we can easily conclude that stannous ions are present in the solution. while if an orange precipitate forms, we can conclude that antimony sulfide has precipitated, while and thereby antimony ions are present in the solution. Then we filter these solutions, precipitates if any formed, and we obtain the filtrate. We boil the filtrate to remove all hydrogen sulfide gas still dissolved in it to prevent the precipitation of sulfides again. Then we add warm dilute nitric acid to oxidize the ferrous ions into ferric ions, because of nitric acid has an oxidizing ability. And then we add ammonium chloride and ammonium hydroxide. We do so to maintain a low hydroxide ion concentration, because these cations can precipitate as they are hydroxides under low hydroxide ion concentrations, because of these salts have a low KSP value. They have a low solubility product. So basically, the ammonium chloride dissociates into ammonium ions and chloride ions, while the ammonium hydroxide ion salt, it reversibly dissociates to form the ammonium ion and the hydroxide ion. The ammonium ion is the common salt. There is a lot of ammonium ions in the solution. Thus, according to the Le Chatelier's principle, the ammonium hydroxide equilibrium shifts to the backward direction towards the reactant side, and a low hydroxide ion concentration will be maintained. If we were to observe a gel white precipitate, it indicates the presence of aluminium hydroxide, and thus we can determine the presence of aluminium ions in the solution. If we were to obtain a gelatinous red-brown color precipitate in the solution, we can conclude that it's the presence of ferric hydroxide in the solution. Thus, we can conclude that ferric ions are present in the solution. If we were to obtain a gelatinous green-blue color solution, then it is chromium hydroxide, and thus we can conclude the presence of chromium ions in the solution. Then we filter the solution, we filter these precipitates if any are formed, and you see the filtrate is basic because of we have added ammonium hydroxide, and then we bubble hydrogen sulfide it again to precipitate these cations as they are sulfides. They need a big sulfide ion concentration to be precipitated. That's why the hydroxide, that's why we do it in basic medium, because of you see in these two equilibriums, the hydroxide ions react with these hydronium ions, these H plus ions, and it will create water, and thus there will be a vacancy of hydrogen ions in this side, and thereby the equilibriums will shift to the forward direction according to Le Chatelier's principle, and thus it will increase the sulfide ion concentration and precipitate those cations that require a high sulfide ion concentration to be precipitated. But by the way, this is the ammonium equilibrium I was talking about. You see, so you can see how ammonium hydroxide reversibly dissociates, and how by adding ammonium chloride we can increase the concentration of ammonium ions over here and shift the direction of the equilibrium to the forward direction and lower the hydroxide ion concentration to precipitate those cations that need a low hydroxide ion concentration to be formed. Moving on, if we were to obtain a black precipitate, it could either be nickel sulfide, cobalt sulfide, or cupric sulfide. Excuse the mistake. Yeah, and try to ignore this. It is cupric sulfide that is formed. If a black precipitate is formed, it could either be nickel sulfide, cobalt sulfide, or cupric sulfide, CuS. And thus we can we can identify the presence of either nickel ions, cobalt ions, or cupric ions in the solution. If a white precipitate were to be formed, we can easily identify that it is due to the presence of zinc ions in the solution. And if we were to obtain a pink color sulfide precipitate, we can identify that it is due to manganese ions present in the solution. Then we filter these precipitates if any formed, and to the filtrate we add ammonium chloride and ammonium carbonate into the filtrate. And via the same mechanism, this mixture will maintain a low carbonate ion concentration in the solution, and thereby these cations, they can precipitate under low carbonate ion concentrations because these carbonates have a low Ksp value. They have a low solubility product. Then all of these are white in color, and if we were to obtain a white color salt, it will either confirm the presence of strontium ions or calcium ions or barium ions. We need to do secondary titrations to know which ones exactly. Then we can filter these precipitates if they formed, and to the filtrate we can do the flame test, in which if we were to observe a flash, we can conclude that it is magnesium ions that are present in the solution. While if you observe a purple or lilac flame, it is potassium ions that are present in the solution filtrate. While if we observe a yellow color flame, we can conclude that it is calcium ions that are present in the solution. Then we'll just do a quick review of the flame test. Basically, if we were to undo the flame test to these cation solutions, lithium solution will produce a crimson red color flame. Sodium will produce a yellow color flame. Specifically, the color is sodium D line. Then rubidium will form a red violet color flame. Cesium will produce a blue color flame. Potassium will produce a lilac color flame. Calcium will produce an orange red color flame, a scarlet red color flame. Strontium will produce a crimson red color flame. Barium will produce a yellowish green color flame and apple green color flame, while copper will produce an olive green color flame. And that is the flame test and the cation analysis. See my finger.